We live in an infinite space where gravity is easily calculated using Newton's law. But what if we lived in a closed space where the whole world repeats infinitely? Would gravity grow to infinity, or would it converge to something? Or how do you calculate gravity on a Klein bottle? And how does a portal to a pocket dimension affects gravity? In this video we will explore not only that, but also the unexpected discovery of self-force, where a body starts pushing itself in the presence of portals. And at the end I'll answer your questions from my previous video. This video is a continuation of my previous video about calculating gravity with portals. I recommend watching it first. Long story short, in the previous video we abandoned Newton's law for calculating gravity, because it's designed only for infinite flat space. Portals bend space, so it can't work with them. That's why we switched to Poisson's equation for the gravitational potential. I explained how I calculated using the finite element method on triangles, and how to add portals by simply changing the indices. As it turns out, portals bend gravity in a pretty interesting way, and they do so in a way that makes perpetual motion machine impossible. And in the portal paradox, option A gets a real logical foundation. So what even is a torus? A torus is this closed space that's depicted like this with arrows. The lines with arrows are portals. That's why I chose this topic. When you enter the top portal, you come out of the bottom one. And when you enter the left one, you come out of the right one. In other words, lines of the same color are connected to each other. This results in an infinitely repeating world, but with a finite amount of space. There are hypotheses suggesting that if our universe isn't infinite, it might be a similar shape that repeats in all directions. Now, to calculate gravity here, let's start by placing a circular mass in the torus space. Then we need a way to tell our method that this space loops back on itself. In the finite element method, the space structure is defined by triangles and the indices of the unknown values they refer to. So we implemented portals as a change of indices, such that the top triangles reference the same unknowns as the bottom ones, and the right ones point to the left ones. This way, the finite element method will see our space as if it's loop-like on a torus. However, there is one very important detail here, specifically the corners where the portals touch. Right now we have different unknowns at each corner. If we visualize the space with this gradient, we can see that all these corners meet at a single point on the torus. So the corners require special attention. So I built a dedicated corner reindexing feature that takes a directional segment like this and remaps all the corners to a new point. I do this manually just by setting a couple of these parameters. This is very important because, as we remember from the previous video, even a very tiny portal point can create enormous gravity. So after we've done all this, we need to solve a system of linear equations. And I do that with an iterative method, so we can see what the solution looks like with each new iteration. Well, it diverges. Gravity just keeps increasing with no sign of stabilizing. So what do we do now? To solve this problem, let's start researching. And this is where the Opera browser will help, the sponsor of this video. Ever have a million open tabs after a research session and forget which ones you just visited? Tab traces help you identify them by highlighting them with an underscore. The darker the underscore, the more recently you visited the tab. But then I remembered that I have snowboarding planned, and I have to find the perfect apartment in another country. This is where another Opera feature helps, tab islands. I can collapse and expand all the research tabs that I organized into one island, and start a new island for apartments. And when I open a link in a new tab, it automatically adds it to the current tab island. And I can color code or rename the islands. But since the apartment map doesn't show snowboarding tracks, I can use the split screen feature to add another tab to the side of the apartment search, so I can see where each apartment is located compared to the trail map. You can have up to 4 tabs open in split screen at once. And then for every apartment, I want to check which ones have a dryer. Checking that manually is very tedious, so this is where I can use the free Opera AI, which not only has access to the page content, but can also work with the whole tab island. So if you want to make your web browsing more convenient, download Opera with my link in the description. Let's start with something I skipped in the previous video: boundary conditions. Any differential equation requires some boundary conditions. For calculating planetary gravity, I used a simple Dirichlet boundary condition. I simply wrote into the equations that the unknown potential at the boundary equals 0. When the simulated area is small relative to the planet, the gravity is noticeably distorted. But as the simulated area gets larger, the gravity starts looking more like the true gravity in a real infinite space. And for space with gravity directed downward, I used Newman conditions. They are more complex, I won't dwell on them here. But on a torus, there can't be any boundary conditions, because there are no boundaries. And there is nothing to limit the potential. So I use one standard trick. We need to apply a uniformly distributed negative mass across the entire torus space, with a density chosen so that the total mass sums to 0. Then we restart the finite element method, and we see that it has converged to a stable picture. So if you believe our universe is closed on itself, then perhaps some compensating negative mass must exist somewhere. Now we can finally move on to the experiments. We enabled the streamlines and see 2 regions of unstable gravity here. One is a point and the other is a line. On the 3-dimensional torus, these spots sit on opposite sides of the mass, each in a different direction. Next, if we move the mass around, we see that the picture doesn't change at all. It just shifts. This means gravity on a torus doesn't depend on how we place the gluing portals. And we can even rotate this picture on the torus without changing the result. By the way, this 3-dimensional torus is actually just a visualization of the topology, not its objective geometric shape. If you want to see what 2-dimensional space on such a 3-dimensional torus would actually look like, check out Artem Yashin's video. I helped out with it a bit. A torus with truly flat space requires a 4th dimension and is called a Clifford torus. Now let's add a second planet, and we see some white arrows have appeared. They show the gravitational force acting on each planet. I calculated them by integrating over the surface of each planet. And in this case, you can see the arrows aren't pointing perfectly towards the centers of the planets, but slightly to the side, because they are being influenced by all other copies. Here is how the arrows change when we move the 2 planets around. Unfortunately, I wasn't able to make these planets move and teleport, so I won't be showing that. The next interesting closed shape is the Klein bottle. You've probably heard of it and know that it actually exists in 4-dimensional space. And when we project it into our 3-dimensional space, it starts intersecting itself. In reality, it doesn't intersect itself in 4-dimensional space. It's just distorted by perspective. Structurally, it's very similar to a torus, but the top arrow points in the opposite direction from the bottom one. This means there's a mirroring portal here. So when you enter this mirroring portal, you not only end up on the other side, but you also get mirrored. And if you ever find yourself in such a world, don't eat mirrored food, it could kill you. There are plenty of YouTube videos explaining why. As for implementation, similarly, we need to remap the corner indices and add uniform negative mass. And there is nothing special beyond that. If we move the planet up and down along this shape, the structure of gravity won't change at all. But if we move the planet left and right, the structure of gravity changes. This means that in such a universe, you could potentially figure out its horizontal size through a physical experiment. And by the way, you can rotate the picture on the Klein bottle in this direction, because nothing changes along it. But you can't rotate it in the other direction because of this asymmetry. And if we add a second planet, the combined gravity of the two planets behaves strangely. And this is what it looks like in motion. The next interesting surface is the projective plane. If you want to dive deeper into this topic, I recommend this video. Here you can see one pair of portals, and they don't just mirror. The entrance and exit have different shapes. One hemisphere is convex and the other is concave. These portals don't obey the surface irrelevance axiom, so many of my results don't apply to them. I consider them portals, but not in the full sense. Maybe in the future I will cover this type of portals in more detail. So they are not classical portals, but when it comes to remapping unknown indices, they work exactly the same way. The finite element method handles them just fine. Topologically, this surface is arranged so that everything that goes into the circle comes out on the other side, and that's true for every direction. And if you send a beam of parallel rays, they'll converge after teleportation. So it works like some kind of portal lens. A neat way to visualize the projective plane is this 3D shape known as Boy's surface. No, this isn't a surface for boys. It's named after its discoverer. This surface has a pretty interesting triple symmetry, and its internal structure is quite interesting too. As for corner remapping, there aren't corners here, but there are points where portals touch, and they require special attention, just as before. Here we similarly remap both contact points to the same point, because that's how the topology works. When we create a planet, we get a picture like this. It doesn't change at all if we rotate its position in a circle, but the picture does change if we move it towards the center. Same story as the Klein bottle. There are two more interesting variants. The first is the projective plane through a square fundamental polygon, which is less natural for visualization on Boy's surface. And the second option is a sphere in the form of a square surface. But I won't go into detail on this. Actually, I took all these closed surfaces from a Wikipedia page called Fundamental Polygon. If you want to look at these scenes and play around with their gravity, it is available in my program Portal Lab on Patreon. Now about the pocket dimension. Many of you asked what gravity would look like in this case. As I explained in this video, to get a pocket dimension, you need to take two connected two-sided portals, make one smaller than the other, and place the small portal inside the big one. And to do that, the shape of their teleporting surface has to be curved in such a way that the small portal can fit inside the big one. Of course, you can calculate that kind of gravity using portals of different sizes. The finite element method can't handle it, and we could even explore how scaling portals interact with other bodies and their mass. But that requires going through the whole theory of scaling portals, and I am not ready for that yet. But there is a way to create a pocket dimension using portals of the same size. In this video I explained that we can use a negative portal for this. A portal whose teleportation surface extends infinitely. Here's what it looks like in a two-dimensional world. From the outside, all light passes straight through it, so it would be invisible. But if you enter this portal, the space becomes looped and infinite. And here's what the exterior looks like from the pink ball's point of view. And here's what it looks like when it flies into the pocket dimension. You can see how everything repeats inside. And here's the topology of this portal. On the outside, it is a regular flat space, and the pocket dimension looks like a cylinder, and the portal is a tunnel connecting a regular space with this cylinder. That's exactly why I call it a portal to a pocket dimension, because it creates a separate chunk of space that can only be accessed through this portal. If you place a planet near such a portal, gravity naturally leaks into the pocket dimension, and any object from the pocket dimension will be attracted to that planet, as we can see from this particle simulation, where all particles escape from the pocket dimension and head towards the planet. Things get interesting when we place a planet inside the pocket dimension and start moving it higher and higher up the cylinder. Gravity along the cylinder seems not to decay at all, but my experiments suggest it just decays incredibly slowly. If we shift one portal higher, the direction of gravity inside the pocket dimension also changes, and seems to follow the direction of the eigenvector of the portal matrix. I talked about this here. Now for the most interesting thing I discovered while researching all of this. I noticed that when I place a planet in the pocket dimension, its internal equilibrium point is shifted relative to its center. What does this mean? Let me show you with an example. When we have just two planets, the equilibrium point inside them is also shifted a bit, because they attract each other. From Newton's law, we know the smaller planet will accelerate toward the larger one more, and the larger one will accelerate less. And this correlates with how the equilibrium point looks inside them. In the small planet, it is shifted a lot, and in the large one, it's shifted a little. I decided to calculate the actual force acting on the planet by integrating over its entire surface, and I got these arrows. They represent each planet's acceleration. Now let's apply the same calculation to the negative portal, and we get an arrow. But why is the planet being pulled somewhere? We don't have any other masses around to pull on it. Is it actually pulling itself? Yes, and this is the unexpected discovery I promised at the beginning of the video. It turns out that a spherical mass in a pocket dimension creates a force that makes this mass move in a specific direction. More precisely, the planet's images through the portals create this force. Let's simulate this effect using a body made of particles and see where it goes. We launch it near the portal, so the body flies toward the portal, then enters the pocket dimension and flies away. And the further it gets into the pocket dimension, the stronger the pulling force. This is a pretty terrifying result. So if we create a negative portal, it will make any mass push itself into the abyss of the pocket dimension with no way back? And given that gravity barely decreases with distance in there, this basically turns into some kind of Newtonian black hole? From what I gathered by consulting ChatGPT, a similar phenomenon exists in electrostatics and is called self-force. It's when a charge creates a force that pushes that very charge in the presence of conductors. I suppose portals act like perfect conductors of gravitational potential, so the analogy fits. Let's explore this self-force in more detail. We will start by changing the radius of the planet to make sure this works for point masses too. I'm changing the planet's radius and density simultaneously, so that the mass stays constant. And as we can see, the arrow doesn't change. So this isn't a macro-scale effect. Next, we need to figure out how to visualize this self-force at every point in space, to understand what it looks like. Just moving the planet around and watching its arrow isn't very convenient. And launching a soft body from every point in space isn't very convenient either. So I decided to just iterate over all possible points in space, place a small planet there, calculate gravity with the finite element method, then compute the surface integral over that planet to find its self-force, and then place a square dot like this that shows the direction and magnitude of the self-force. This takes a very long time because the finite element method is fairly slow to compute. And here we need to compute it exactly 10,000 times. As far as I can tell, there is no mathematical method that lets you compute this for the entire space at once. The way it's done with Poisson's equation. So we just have to wait a very long time. But you won't have to wait thanks to the magic of editing. And we end up with a picture like this. Clearly shows that the strongest self-force occurs inside the pocket dimension and stays roughly the same there, meaning a body in this pocket dimension will accelerate forever at a constant rate. Since this is a Newtonian model, there is no speed limit. Next, we see that near the portal, the self-force pulls everything inside. But at a certain distance, the negative portal creates a repulsive self-force. Poof, so this Newtonian black hole won't immediately suck everything in the universe into itself, only whatever gets too close. Alright, the pocket dimension case is clear. Let's look at the self-force of other portal configurations. This is just flat space. Here the arrows point in random directions due to numerical error, because infinite flat space has no self-force. Now here's what the self-force look like on a torus. Judging by the arrows, there is no self-force here either, so it is an excellent analog of infinite flat space, but without the infinity. And this is the self-force for the Klein bottle. Look at these distinct vertical lines of stable self-force. Everything in such a universe would be attracted to these lines and stay near them. Very interesting. Yet another way to tell when you are living on a Klein bottle compared to other spaces. And self-force for the projective plane looks like this. Here everything gets attracted from the center towards the edges. Most likely this happens because all the curvature of this space is concentrated at the edges, while the rest of its space is flat. Okay, but is there self-force between regular portals? Here's what it looks like for a pair of portals. And here we see a pretty interesting thing. The portal edges create a repulsive self-force. And if I rotate the portals, the behavior stays roughly the same. So it turns out almost any portal configuration, except for a torus, creates some kind of self-force that makes bodies push themselves in certain directions. Maybe this has something to do with the fact that portals change the topology and break certain symmetries, similar to how the law of conservation of energy doesn't work in an expanding universe. Let's start with one of the most frequently asked questions. Will light be bent because portals bend gravity or bend space? No, we are considering Newtonian gravity, where gravity doesn't affect light at all, and portals bend space while keeping it flat. So portals will still look like magical doorways to other worlds. Next, a lot of people asked what would happen if you rotate the portals. Nothing special, the body will just take a longer trajectory downward. And if you place them at the same height, they'll change gravity in a clearly noticeable way compared to non-rotated portals. And a body here will behave like this. But you can also rotate portals by 90 degrees. And I want to show this simulation in that regard. Here the portals are placed at different heights, and we want to use one portal to get to a higher elevation. But if we throw an object into the lower portal, it will be repelled with a strong force. It's very hard to enter, and if we place an object near the upper portal, it will roll into the lower elevation. And this is just a small height difference, yet already such a huge difference in gravity. The greater the height difference, the stronger the effect. So it turns out portals that teleport gravity are pretty useless in practice. There is no point in making a game with them. You literally wouldn't be able to go anywhere. And if we place such a portal on the moon, the lunar soil would get sucked into the portal very quickly and sent to Earth, because the potential on Earth is very different from the moon's. So these portals can only be used at the same height or placed in space far from gravity sources to minimize the different potential effect. And now the answer to the most discussed question from my previous video. Does my fourth axiom about portal size really hold up? Yes, I got the terminology wrong. It's more of an expected behavior than an axiom. A lot of comments said my intuition was wrong, and that as portals approach zero size, they should still have a measurable effect on gravity, because they glue together areas at different heights, meaning different potentials, so their influence on gravity will always be noticeable. Then one day I opened my inbox and found an email from someone called Fine Geometer, who'd worked out an analytical way to compute portal gravity using complex analysis. I opened the attached document and there's a PDF with mathematical calculations. This is what I love about my community. You solve things I can't and point me toward ideas I wouldn't come up with on my own. Thank you for that. I'll put his calculations under this link in the description. But here are all the pages from those PDFs, in case you'd rather just read everything right here on screen. And according to his calculations, the influence of portals on gravity really does approach zero, but at an inverse logarithmic rate, which is insanely slow. So my intuition didn't let me down, and a whole lot of commenters turned out to be wrong. So folks, the final word always belongs to the math. Also in these documents, he showed that gravity near a portal edge really does grow to infinity. And there was a lot that didn't fit into this video. Gravity of a monoportal, gravity of a triple portal, the physics of scaling portals, gravity of a portal in a portal. But all of that can be explored in my program, which is available on my Patreon. For now, I just want to give a massive thank you to everyone who's already supporting me. That's all from me, thanks for watching.